Okay, we have another problem here dealing with applications of Extrema. Assume that a wooden beam has a rectangular cross-section of length L and width W. The strength of the beam is directly proportional to the length and the square of the width. What are the dimensions of the strongest beam that can be cut from a round log of diameter 24 inches? So here's your diagram. You can pause the video at any time if you want to try this. I'm going to let S be the function of strength, and I'm going to use, instead of X, it's going to be a function of L. And it's set up by the proportion that was given. It's directly proportional. So we have a constant K to the length, as you see there, the diagram, length L, the square of W, the width. So we can see here that W squared plus L squared is equal to 24. And because the diameter of this cross section is 24, we have to have L somewhere between 0 and 24. So L is greater than or equal to 0, less than or equal to 24. That'll be the interval we're looking at here for the in this case, we're looking for a maximum, maximum strength. Now W squared, I'm going to solve for W squared here in this equation. And of course here I use the Pythagorean theorem. These are right angles here. This side over here is L also. So L squared plus W squared equals 24. So W squared, the same thing as 24 minus L squared. So this expression right here then, the function S of L can be given by the constant, and we don't know what this constant is. All we know is a positive number since it's directly proportional. And then we got L, and then W squared can be replaced by 24 minus L squared. So this will be the constant here, K, multiplying through by L. We get 24. And I made a correction here. It's to square this 24. So that's 576 here, and here, and in here. So then just multiplying through by L there, this will give us 576 L minus L cubed. And this then would be the function, the strength function S of L is equal to this quantity here. Anyway, that's the way you started off. So maybe you can read it better this way. So there's your function S equal to KLW squared, and then we have W squared plus L squared is equal to 24 squared, which is 576. And we solve that for W squared. So in place of this W squared, I can replace it by 576 minus L squared. And we get this right here. Now it's just a matter of computing the derivative of this, the derivative, and I'll leave the constant out here. Just take the derivative of what's inside there, that's 576. Derivative of 576L is 576. And again, we're differentiating with respect to L. And then this is going to be 3L squared. And then this is your derivative. You want to find the critical numbers, so we want to set this equal to 0 and find the critical numbers. Obviously we can divide through by K, and we're going to have then 576 equal to 0. Let's solve it with 3L squared. Divide both sides by 3 and we get 192. Now you can simplify that as 64 times 3, so the square root of 64 is 8. We get 8 times the square root of 3. We'll just go ahead and leave it as a decimal. Take the square root of 192 and you get 13.9. And of course that could be plus or minus, but in this case, of course, a negative is not going to be in this particular interval. The zeros, the endpoints 0 and 24 again are not feasible in this kind of situation. So 13.9 is the only critical number. So pick values larger than 13.9, say 14, plug it back into the derivative. It's going to be negative in here. plug in a number less than 13.9, say 13, plug it into your derivative, it'll come positive. So again, derivative positive to the left of 13.9 and negative to the right. So that tells me the graph is rising, reaches a high point, and then it comes down in that interval. And that is the only critical number. The derivative is always defined, so there are no values for which the derivative is undefined. So this would tell me then that the dimensions that will give us a maximum strength will be 13.9 for the length. So the dimensions that give us maximum strength will be 13.9 for L and 19.6 for the width. And this is in inches. So again, you have your formula here. You know L, you can plug it in there. Solve for W. If you leave these in radical form, you have 8 for this one times the square root of 3 for L. And for the W, it's 8 times the square root of 6. Again in inches. Thanks for watching. We'll see you next time.